In November of 2018, the Real Engineering channel made a video titled "The Truth About Vinyl," talking about vinyl recording. And Real Engineering got some things really wrong in this video. Now, their video is very good. I recommend watching it if you haven't seen it already. I do have it linked in the description below, but they did make some glaring errors, and I'm going to address those now. Let's start by looking at the first one, which is the microphone.
The simplest of these would be the microphone, which turns air pressure into either a digital or analog signal.
The problem with that is no microphone has a digital output. Yes, they do make digital microphones. I have one right here. I use this one whenever I'm not appearing on camera. But this is an analog microphone with a built-in A to D converter. So microphone, A to D converter, and then we have a digital output. But the microphone is not digital. Let's take a look at how a microphone works so we can understand what it does. There are many types of microphones. There are ceramic microphones, which are piezoelectric, meaning that bending of a crystal creates different voltages. There are condenser microphones, which are the most common these days, which use a capacitor, and changing the distance in the plates of those capacitors changes the voltage on it. There are also ribbon microphones common in professional recording, but I think the best microphone to demonstrate what a microphone does is a dynamic microphone. And that starts out with a magnet, which has a profile something like this. This is a side view, and this would be like a north pole, a south pole, and a north pole. And if we look down upon it, it would be circular, and this would be the view looking down, where we have the North Pole and the South Pole and the North Pole. So it's North Pole all the way around, with the cylinder in the middle being a South Pole. And suspended in here is a spool that is wrapped with copper wire going around that pole there. So that's going round and round there. And that copper wire would have its ends coming off, suspended in some way so that it's free to move. And this would be connected to a diaphragm that vibrates with the air, which is loosely coupled to the frame of the microphone, so that the diaphragm and the copper coil that's connected to it can move freely. And when you move a wire through a magnetic field, you get an electrical current. So when this is being pushed down by a sound wave, it's going to create a current that goes one direction, so like in there and out there. And then when it's moving the opposite direction, that current is going to reverse direction and go out where it went in and go in where it came out. So we get two different directions of current. So as this vibrates, it's going to create an alternating current going back and forth that is at the same frequency that it is vibrating, which of course is the same frequency as the sound that's hitting it. Frequency being how many cycles per second. High cycles per second, or high frequencies, are high pitches. Low frequencies are low pitches. So that's what the microphone is able to pick up and turn that into those electric currents. And what they show coming out of the microphone, this wave, this is called a wave because that's what it looks like, but it's actually a graph of the current coming out of the microphone. If it is a current-based microphone like this, other ones are voltage-based, but if we take this line here as 0 amps of current, when this coil has the greatest velocity, it's going to have the greatest current. So when it's at the greatest velocity in the middle of its motion, we're going to get our greatest current, and there'll be some number of microamps. And when it reaches the end of its travel, when the sound energy is starting to pull it back instead of push it down, it's going to be at 0 amps because it's no longer moving. It's only when it's moving does it create the current. And then when it reverses direction, the current's going to go the opposite direction. So this is the current going one direction, that's the current going the opposite direction. So we have a positive current and a negative current. And negative current just means it's going the opposite direction. So positive current goes this way, negative current goes that way. That's all it means. So as that diaphragm goes back and forth, we get this current that increases, decreases, increases the opposite direction over and over again, creating this wave. And this represents a sine wave of a single frequency, which I guess that's redundant because a sine wave by definition is a single frequency.
Yeah, I guess that is the same thing.
But as this vibrates faster, these waves would happen faster. And if it vibrates slower, they would happen slower. So this is time and this is amplitude of the wave. And if the wave has more amplitude or is louder, it's going to be bigger. And if it has less amplitude or is quieter, it will be smaller. And I'm going to erase this just to give something more realistic, because that's looking as if we have a test wave going in there that's only a single frequency. What we would really get out is something that looks maybe, who knows what it would look like. Whole bunch of different frequencies, probably with some kind of a repeating pattern, because, for example, when I'm speaking, I'm creating a number of frequencies anywhere from maybe 100 hertz to 4,000 hertz, and they mix together to make a complicated wave that looks, who knows what it looks like. I'm just kind of making something up as I go along here to give a better idea of what would come off of that microphone. So the microphone diaphragm vibrates to the sound waves, makes the coil move in the magnetic field, which causes a current that is proportional to the sound waves and what Alexander Graham Bell called voice-shaped currents. So that is how your microphone works. Now, to get a digital output, I have to run that into a analog to digital converter. So what comes out of your microphone and your single wire, which if we have a ground somewhere to simplify it, is going to be our wave, which I'm once again representing with this graph of something going up and down, which just represents the current going back and forth, into an analog to digital converter. And this samples the changing current many, many times per second. For high fidelity audio, it's going to sample probably 44,000 times per second. And what will come out is a signal, which if it's a serial output, it's going to be a series of voltages going up and down. And I'm not going to try to draw too much of it because there's so many different ways to represent a digital output, a digital serial output, but it's basically going to be turning on and off very rapidly to produce a digital output. If this were a parallel output, which might be what you have in a computer, there's going to be probably as many as 16 wires out here with different discrete voltages. Well, 0 volts and 5 volts would be a good example. Each wire having either 5 volts or 0 volts on it at any one time, giving you 65,536 possible combinations of 5 volts and 0 volts to give you a digital output that could be taken into a computer. But once again, for example, the microphone I held up has a serial output, so it'd be basically turning on and off in that wire very rapidly with a pattern of ons and offs that can be deciphered at the other end and made use of. So that's what a microphone does. Analog microphone, all microphones are analog. If you have a digital microphone, you're going to have an analog to digital converter, and now you know how a microphone works. So now let's take a look at the really biggest glaring mistake in the entire video.
As the stylus follows the groove, it moves the magnet wrapped in a small coil of copper wire. This causes an electric current that corresponds to the groove on the vinyl.
Yeah, what was that about? Okay, what they showed was the tone arm and its pivot mount here where it's able to pivot and go up and down, our pickup at this end, and what was that at this end here? That is a counterweight. This is relatively heavy, and to counterbalance it, they put a counterweight on there, and this can be adjusted to give just the right weight on the needle as it rests on the record. So what were they showing over here? They're showing a magnetic pickup over here? Absolutely not. That's nothing but a counterweight. So what they showed was simply entirely bogus. So what actually happens is all the processing happens up here in the cartridge. And since the Audio-Technica advertising materials of many years ago used to illustrate their arrangement of magnets, I have that in my head so I can draw that for you. So looking from the side, there was a rubber mounting with a couple of magnets on it, and then a metal bar which went down, and pressed into it was a diamond or sapphire stylus. And if I draw this from a more practical angle, looking at those magnets, they are little cylindrical magnets, greatly enlarged here of course, 45 degrees off of vertical but 90 degrees apart. And so we have the stylus coming down to the front and into the groove of the record. And the stylus, now if we take a better look at it here, in the groove of the record, pretend that's 90 degrees if it isn't quite that way, the stylus comes and contacts that side and contacts that side. And one of the stereo channels is encoded onto this wall, and the other stereo channel is encoded on this wall. So when this wall moves, that's one of your two stereo channels. That moves the stylus that way, so the stylus is moving this way, causing this magnet to move the same direction. So one channel makes this magnet move. The other channel is encoded into this wall, and it moves in that direction, causing the needle to move in the same direction. And so that would cause it to move this way, causing this magnet to move in that direction. And around the magnet is a ferrous metal with a coil of wire wrapped around the end. And this works a lot like the microphone I just described. Except here, instead of moving the coil of wire in the magnetic field, we move the magnet, but we have the same effect. The moving magnetic field causes an alternating current in this coil here that is directly proportional to the movement over here, which is what's encoded into that wall. And we have exactly the same thing over here of the ferrous metal and the coil. And so when this wall moves, it makes this magnet move, and we get a signal over in this coil over here. And it works, again, pretty much like the microphone, causing one channel to be over here and the other channel to be over there. And of course, that runs down some wires down the tone arm and somewhere goes into the system to be processed and amplified. Now, there are other ways to make the cartridge. This would be a type of dynamic or electromagnetic cartridge. And once again, this is the arrangement that the Audio-Technica cartridges use. But other ones might have moving coils and stationary magnets if they are a dynamic or magnetic cartridge. Others would have piezoelectric crystals attached to the needle in one way to get the signal out. But this is the basic idea of how a pickup works. So that is all built into here. If I can draw it really tiny with this giant pin. And with the Audio-Technica, the entire stylus and mount and magnets is removable so it can be replaced, and the pickups remain in the cartridge. So that is how the pickup works. And so what about back here? Showing the signal going down the tone arm to a magnet back here with a pickup coil in the back was simply totally bogus. Nothing but a counterweight back there.